all and welcome to this lecture. We are in module 9, lecture number 4, hot carrier effects. In this lecture, let us see a few more effects which is coming in short channel devices and how they are affecting the theory what we developed for long channel devices. Out of which we will discuss hot carrier effects, velocity overshoot and ballistic operation. These are the learning outcomes of this lecture which helps you to understand what do you mean by hot carrier and how it affects the MOSFET operation when the channel length is small. Second, we will discuss about the velocity overshoot effect and how this velocity overshoot and ballistic transport phenomena is affecting your modeling approach and the operation theory of scaled MOSFETs. So, let us do a quick recap. In previous lecture, we were discussing about Dibble and said that this is more pronounced and important short channel effect, which is nothing but the alteration or modulation of source channel barrier because of applied drain voltage. We said that if the channel length is very much small, then when you increase drain voltage, then the electric field lines emanating from the drain side will go away to source channel barrier and hence it alters this barrier height. In turn, the threshold voltage of the device becomes a function of VDS. In long channel devices, we said that the threshold voltage is solely captured by VG, obviously with VSB. However, in case of Dibble or in short channel devices, the threshold voltage becomes a function of VDS. We solved two dimensional equations also to find out what is the change in threshold voltage due to Dibble, which was explained by this equation, and we also said that with some good amount of approximation we can see that Vt Dibble can be represented as beta 4 plus beta 5 VSB into VDS divided by L to the power of beta 6, where beta 4, 5 and 6 are constants and VSB is source to body voltage. We said that when you increase the doping concentration of the substrate, Dibble will decrease, and when you increase VSB, then the expansion of the depletion region will be more and hence Dibble will be more. In addition, we have discussed that there are two types of punch through, which is surface punch through and bulk punch through. Unlike Dibble, the punch through will not only change the shift in the threshold voltage or the shift in the IDVD characteristic, IDVGS characteristic. Instead, it will alter the device behavior in the sense the trend of the characteristic. We said that in punch through the gate will lose its complete control and hence the I/N-off ratio reduces significantly. Ratio reduces due to punch through. In addition, we have seen how we can incorporate the said short channel effects in our model which was derived for long channel devices with minor modifications. In this lecture, let us see what is hot carrier and what are the effects of hot carriers in MOSFET operation. In general, the movement of electrons governed the transport of the current in a very interesting fashion. Means it is completely statistical in nature. What it means is, suppose an electron is leaving the source and then it will gain the energy from the electric field, it will get accelerated and then it will lose the energy through scattering. So, throughout this journey the electron will gain the energy, accelerate and lose the energy through scattering events. We have already discussed what kind of scattering events is available in the MOSFET, right. So, in this process let us consider if the channel length is small enough and hence with some voltage we applied VDS equals to VDS dash, the channel in the channel the complete charges reaches to velocity saturation. So, the carrier which is moving from the source, it is velocity saturated, and with the maximum velocity the carrier is moving from the source. The moment the carrier will come near the drain, it will acquire the energy because of high field, because here near the drain you can see you do have Pn plus junction, and at the junction you have a very high field present into it, right. So, the carrier which is coming with a higher velocity or the maximum velocity gain enough energy, thus the random component of its energy is increases. Thus, this high energetic electron will gain some energy, and then when these carriers impart with the silicon crystal or silicon lattice, it breaks the bond. At this condition there will be a electron hole pair generation takes place, EHP. The electrons or the carriers which acquire enough energy from this depletion region field, this is called hot carriers. When the moment EHP generated, the hole will attracted toward the substrate because it is either 0 or positively biased, whereas the drain is connected to positive terminal, and hence all the electrons will go this side. These electrons will contribute or join the stream of the electron which is coming from the source. So, these are the additional electrons generated in impact ionization process. This process is called weak avalanche. Here the same amount of holes will coming towards the substrate, and they constitutes a drain to body current. So, if we want to represent this drain to body current with respect to terminal voltage, we will find that drain to body current shows this kind of behavior. We can understand like this: if you increase VGS, then you are increasing IDS, and increasing in IDS ultimately increases the IDB. But at the some point of increasing in VGS, ultimately you are moving from saturation region to non-saturation region. Because of that, the effective voltage near the depletion region reduces, and hence the drain to body current reduces because impact ionization reduces. So, what happens is, earlier the carrier were coming from the source, it acquires energy from the field, becoming hot carrier and causes an impact ionization in the depletion region. There was be E and H generated, means electron hole pair generated. Electron went towards drain side, joined in the stream of IDS, and hole went toward the substrate. The drain to body current thus is directly proportional to drain to source current, because the same amount of electron is which is contributing into the main stream of drain to source current is the same amount of hole is coming towards the substrate. So, we can simply write IDB is directly proportional to IDS. So, a small increase in gate voltage increases IDB, but the moment you increase VGS, ultimately you are reducing the effective voltage drop here, because the effective voltage drop here is what? VGS minus VGD, and that is what you are moving from saturation to non-saturation region. That is what the impact ionization will be loosened, and hence the generated EHP will be reduced, so that IDB will reduced. Correct? We can simply find out a closed form equation of ID in terms of IDS by considering few approximation. Let us consider that this is my structure, N plus are source and drain, and here there is a depletion region. We are assuming that the electrons which are coming from the source, they are coming in a laminar way, in the sense the stream of the electrons is exactly parallel to the interface. The second thing is, we are assuming this flow is even parallel in the pinch off region, because we have seen when we were discussing about channel length modulation, this flow was somewhat like this. It will go away from the surface in the pinch off region. However, for the sake of simplicity, we are assuming that the flow of the carrier in the pinch off region is also parallel to the surface. The second assumption, we are assuming that here only the primary impact ionization taken place, meaning the carrier which are coming from the source will only cause the impact ionization. Once electron and hole pair generated, these electron hole pair will not again cause the impact ionization. Under this condition, we can derive the relation between IDB and IDS. Let us consider a small fraction of length delta x, over which we can simply say the change in the IDB, which is delta IDB as a function of x, is nothing but alpha n x into IDS into delta x, where alpha n is impact ionization coefficient, and this impact ionization coefficient can be given by an e to the power of minus bn divided by Ex, where Ex is the electric field in x direction. Again, this is x direction and this is y direction, where An and Bn are constant, having 10 to the power 6 per centimeter and 10 to the power 6 volt per centimeter values respectively. So, we can consider this is very small, and we can convert this into an integral, so that IDB can be written as IDS, which is constant, integration of L minus LP to L alpha n x dx, where this expansion is LP. We have already discussed the significance of LP when we were discussing about channel length modulation. So, if we integrate from this edge, which is L minus LP to LP, will actually covering all the charge carrier which is generated in that region due to impact ionization, and hence we can get IDB. So, the overall current through the MOSFET between terminal to terminal will give you what? ID is equals to IDS plus IDB. That is what in long channel device we haven't considered this hot carrier effect, and we haven't considered the impact or the role of IDB. If you remember, we started our long channel theory with considering that body current is 0, but here you can see we do have a drain to body current, and that is significant amount. That is what we are considering this current in our total current. Now, this current causes problems like channel breakdown. Now, what is channel breakdown? In the same structure, if IDS is increases by increasing the drain voltage, let us say beyond VDS dash, then IDS will increase. If the IDS will increase, right, I am sorry, I am making a direction in this direction, the IDS direction will be from drain to source. Everywhere the direction of current will from drain to source. So, this direction flow is the flow of electrons. So, the electrons are flowing from source to drain, and hence the current will be from drain to source. Now, when the electrons are coming from this side, from source side to drain side, by increasing the voltage, then what will happen? They will cause impact ionization here. Because of impact ionization, the stream of electron hole pair further generated, and it will further increase IDB. If the IDB is increases, ultimately the total drain current, which is nothing but IDB plus IDS, increases, and again this current increases, again the impact ionization increases, meaning what? The channel current is expected to increase. That is called channel breakdown. So, the current what you are expecting is this, but you will get this current because the junction current is increases due to impact ionization. There is another problem associated with the same thing, which is called snapback. If you see the same structure and consider that you are increasing VDS beyond VDS dash, so the current will increase in this direction, which is IDS. Now, meaning your electron will come from source to drain side, and hence they cause an impact ionization. As we discussed that they cause an impact ionization and generate electron hole pair. So, the whole direction is this side and the electron will go this side and join the stream of main current. Now, when the whole current is coming up, this give rise to IDB. Remember or make sure this is p type semiconductor in NMOS. If it is p type, locally because of this IDB and the inherent resistor of the semiconductor, there will be a drop in the substrate and that drop will be positive. Now, if I just sketch a adjacent or inherent structure of N, P and N, it looks like this is N plus region, this is P region and this is N plus region. So, it is similar as an NPN BJT which is forming inside the substrate, right. This is N plus which is drain, this is N plus which is source and this is substrate which is body or p type semiconductor. Now, when you increase the drain voltage, IDS increases, impact ionization increases, IDB increases and the voltage drop in the p side semiconductor increases. It means the base of that BJT voltage is increases, and let us consider the current is going from drain to source. So, this is the direction for current, this will termed as emitter and this is collector, right. So, the base to emitter voltage will increase, this become forward bias. If it become forward bias, it means what? It will support IDB to flow. If IDB increases, again what happens? ID increases. If ID increases, impact ionization increases and again IDB increases, meaning there will be a positive feedback occur. Because of the positive feedback, there will be a snapback effect comes into picture. If you sweep ID and plot for VD, you will get this kind of behavior, which simply says that a huge amount of current is observed for lower amount of VDS because of positive feedback. Because you need not increase VDS higher, because of this inherent BJT operation, there will be a positive feedback and the current increases at a lower VDS. This is called snapback effect. Now, let us see another effects in terms of velocity overshoot. As we have said that the carrier velocity and the carrier is be a part of transport phenomena in a statistical way, right. It means the carrier gain the energy from the electric field, accelerate, loses its energy through the scattering, and this kind of statistical behavior of the carrier can be explained in terms of free path or mean free path and free time and mean free time. It means we can simply say the path travelled by the electron before two excessive collision is called free path, and if we take an average of these is called mean free path. We have discussed this concept when we were discussing about drift phenomena in our module 1. This is called mean free path. Similarly, the time taken by the carrier to travel a path between two successive collision is called mean free time. Now, let us assume that we do have a MOSFET having a dimension or a channel length lesser than the mean free path, meaning the length is either small or comparable to mean free path. Then the carrier which is originating from source and moving towards the drain will not encounter an scattering event. So, the carrier velocity of that the carrier velocity is higher than the thermal velocity. That is what is called velocity overshoot. The velocity overshoot temporarily increases the current, but it also increases the hot carrier stress. How? Because we know that the current is can be given by W into V. Now we are writing overshoot. So, this is not a drift velocity. We are not giving that much scattering to that carrier so that it will attain a drift velocity. The velocity overshoot, it means it is higher velocity into minus of Qi dash. Because velocity increases, that is what the current increases for some a fraction of time or in a transient way, but it also increases the hot carrier effect because of the said phenomena what we said as snapback or channel breakdown. We can also understand the ballistic transport in relation with velocity overshoot. What we said is that carrier velocity attain its maximum velocity, but because of multiple scattering event it attain to its drift velocity, right. And when we were discussing about the velocity saturation, we said that when you increase VDS due to effective channel length is short, throughout the channel we do have velocity saturation occur. And let us consider the carrier which is emanating from the source is having velocity saturated or it attains VD max. This ballistic transport phenomena can be explained by this Venn diagram, which was a result of Monte Carlo simulation. This is a simulation approach which helps us to track the behavior of individual electron. Here blue dots shows the electron. Now this solid line shows the conduction band edge plotted along the channel length. It means this side is source, this is channel region and this is drain region. It is clear that in the source the electron does have finite energy which is available in the conduction band. A few of the electron can cross this barrier after barrier lowering, what we discussed in drain induced barrier lowering, and these electron will come here. Now because of this electric field, this electron will move towards the drain. You can see some of the electrons are having higher kinetic energy. This line, the conduction band edge, shows the potential energy of the electron. Meaning the difference, the vertical difference from this solid line is shows the kinetic energy. You can see from this simulation graph that the electron which is here having higher kinetic energy than the electron which is present here. So at location A, the electron having higher kinetic energy as compared to location B, which is close to conduction band edge. So in some sense, when you apply VDS, Q times of VDS, then the electron will move from this side to this side, gain enough energy from the field and move towards the drain. During this journey, some electron loses their energy and go near to the conduction band edge. However, some electrons will not lose its energy because they are not coming in interaction with scattering, and hence they maintain the same kinetic energy, and obviously they are coming with saturated velocity as we discussed here. So ultimately this high energetic carrier is coming and reaching to the drain. This is interesting to see that in the drain also we do have carriers which is having higher energies. So if you reduce the voltage, let us say to 0, ultimately the picture will look like this, and we do have carriers here, we do have carriers at the drain. They can go in the channel, but as there is no potential difference coming up, there is no current. Now we can simply model this ballistic transport using our basic model, only changing with the velocity component, because we know the current is can be given by W into V into minus of Qi. So instead of writing drift velocity here, we are writing effective velocity, which says that if there is no scattering event involved in the process, if the channel length is comparable to the mean free path, then the effective velocity will be higher. It will not be same as the drift velocity. So instead of writing Vd, we can simply write E effective, where V effective, sorry, it is V effective. So V effective at 0 is nothing but B times V injection 0. So we are keeping this point as 0 point, which can be called as virtual source. What it means is, this is a source, the carrier took some amount of energy, the carrier gains some amount of energy and it reaches at this point. After this point only, the carrier will come in the vicinity of the channel and accelerated because of the field. So, this point can be called it as virtual source. So, what we see, this point is defined as 0. So, I can say the velocity which is effective velocity at 0 is nothing but injection velocity at 0. Now, this B factor is defined as ballistic efficiency factor. If suppose B is equals to 1, it means with the same velocity with which the electrons leaving the source, it follows the same velocity and enter to the drain. However, due to multiple scattering event, the value of B will reduce. In general, in modern devices, the value of B is 0.6. The value of B is also depend on back scattering. What it means is, suppose a carrier is here at the virtual source and it tries to leave the source, but there is a possibility that the electron will go back to the source. That is what back scattering, and obviously this back scattered electron will not contribute the current. So, we can simply model this ballistic phenomena in terms of velocity, and ultimately we can replace the Vd from our basic equation in terms of V effective. So, in that sense we can try with an effort to preserve our basic models which we derive for long channel devices and include the ballistic transport. But strictly speaking, it is just a simpler approach. It will not give you, it will not guarantee you the exact results, because the phenomena of ballistic and the mean free path and the scattering is completely statistical. So, let me summarize this lecture. In this lecture we have talked about hot carrier effect, channel breakdown, velocity overshoot and ballistic transport. If you see, these all phenomena are related with the carrier velocity. What we said is, if you have a MOSFET and length is very small, then the carrier acquires the drift velocity, it will move from the source, and when it reaches the drain, it will accelerate it by the field. Because of the acceleration, its thermal component increases, and hence this carrier is called hot carrier. The high energetic carrier will come here in the depletion region, causes impact ionization, generated electron hole pair. These electron hole pair ultimately get reflected or attracted because of the significant polarity. The electron will go towards the drain, hole will go towards the substrate. The stream of hole will give you IdB, and the stream of electron will ultimately add up with the main drain current. So, I can simply say IdB is directly proportional to IDS. We derived a closed form equation of IdB in terms of IDS also. Then we said that if this phenomena is happening continuously in the channel, there is huge amount of impact ionization take place and the channel breakdown occur. So, the current is significantly increases. There is also a snapback action which is due to internal parasitic BJT action present between source, substrate and drain. At last we said that due to ballistic operation, the effective mobility is changes, and we need to incorporate the ballistic operation by considering effective mobility instead of writing the equation in terms of drift velocity. So, we will stop here for today. Until then, take care.